Welcome to a lesson with Dr. Powell. Let's look at an application problem where we're trying to build a little pen or fence, but it's pretty small. Let's suppose we have 20 square feet in here, and we know that these sides cost $10 per foot, and these sides over here are $20 per foot. So what should we put here and here to minimize the cost? Well, let's suppose this is X right here length, and this is Y. We know that X times Y is, X times, Y is equal to 20. But what we're interested in is minimizing cost. That minimum should tell us something. Whatever we're trying to minimize is exactly what the output of the function is. Our goal is to make a function, and the output is determined by what we're minimizing. The object of minimization is cost. So here, cost would be the output of the function. We don't know what this function will be. It'll be a function of one variable. All we do for starters is just write down any expression at all for cost, even if it has more than one variable in it. And then we reduce it to one variable after that. We need something to work with for starters. So let's see, what's the cost of this side length? Will be 10 times X, but then you double that because you have this side length down here as well. All cost the same amount. So let's do, so that would be 20X dollars for these two sides. And then similarly for these two would be 40Y. We know in particular that Y is equal to 20 over X. So we could replace this Y with 20 over X. We have a function of cost. Now, and then we can rewrite this as 20x plus 800 over x. Now, if we want to find the maximum of this cost function, or a minimum of this cost function rather, we want to see where its derivative changes sign, and we can see that by particular where the derivative is undefined or where it's equal to 0. So first find the derivative, then set it equal to 0. It looks like the only place it might be undefined is at 0, but that's not really, doesn't really tell us very much. So, so let's try to find out what the derivative is equal to 0. First, we take the derivative 20, then minus 800 over x squared. We set this equal to 0 and solve. Notice that's a lot like saying 20 is equal to 800 over x squared, which is the same thing as saying x squared is equal to 40. Just divide, multiply, which is like saying x is equal to the square root of 40. So if x is equal to the square root of 40, then which we can rewrite as 2 root 10, then since x times y is equal to 20, the only way to offset that to get 20 is to multiply by a square root of 10 to make 20. So y must be square root of 10. So we have our dimensions, and we hope that this will minimize it. Well, how do the signs change around this particular value of x? X is equal to 2 root 10. So, or square root of 40, perhaps. Okay. So let's see here. So this is the derivative itself. So let's think, if x is a little bit bigger than square root of 40, then this denominator will be a little bit bigger than 40. If this denominator is a little bit bigger than 40, then this guy right here will be smaller in absolute value than it was. So that means, it looks like it'll probably be positive then, because you're subtracting of something that's smaller. So it looks like on that side you probably have something positive, and with the reverse idea minus. So that kind of converts you going down then up, so you get a minimum here. Kind of think about that for a minute. If you want, you can actually plug in the value and actually see if you get something positive and negative for sure, but we can be guaranteed that we have a minimum, and it happens right here at these dimensions. Of course, you could find the cost by plugging these back in, but here, let's just figure out the dimensions that give us the minimum cost. Thanks for watching.